To my YouTube channel. Today we shall be looking at this paper, photorealistic single image super resolution using a generative adversary network. Essentially, today we'll be just considering the high level overview of what this paper is. In subsequent series, we might look at some important components of this paper. One thing is that as at this time, the problem of generating high resolution image still persists. So this architecture is an approach to solve that problem. And we just look quickly at the overview of what the paper is about. Super resolved image is almost indistinguishable from the original. So this is the original image, and this is what the SRGAN generated, the network that they proposed. Okay, you could see the original here too, and you could see the SRGAN generated. So from that you have the bicubic interpolation, deep residual network optimized for SLE, deep residual generative adversarial optimized for a loss more sensitive original HR image. And they measure the quality with PSNR and SSIM in brackets. So the PSNR is this, and the SSIM is this. That's another thing we're going to also look at. We'll look at what is the meaning of all this measurement, these metrics, in subsequent series. Okay, so let's go to the architecture they use. The architecture they used here is, this is the generator, this is the discriminator. Now you will see that they make use of the residual blocks, and say you have residual blocks, you have the skip connections, and you have the element wise summation on the generator side, and in the discriminator side, these are the blocks of convolution that was used. The K stands for the kernel size, the N is the number of filters, or feature map, then the S stands for the strides. They use the perpetual loss, the VGG loss, the content loss. We'll look at all that in subsequent series. Okay, so let's go now here to a more discussion about this paper. So the SRGAN is used to generate photorealistic images. This can generate super resolution image from low resolution image with finer details, high quality, and that is what is implemented in that paper. So we'll look at how to implement the SRGAN quickly. So it has the generator network and the discriminator network. They are both deep. So the generator network says a low resolution image of a generator of dimension 64 by 64 by 3. You can actually use any dimension here, but that's specific to what you use. And 3 represent the channel. So as you can see in the architecture here, if you look into the architecture, so this is the generator network. Okay, then and after a series of convolution and upsampling layers, that generates a super resolution of shape 256 by 256 by 3. So that's what we have in here. Okay. Now the discriminator adversarial takes a high resolution image and tries to identify whether the given image is real or fake. So what's the architecture? That's what we showed us before. That's the architecture we showed in the paper. Yeah. So what is this ISR? We will see that. So both the network are deep. They contain convolution of sampling layers. Each convolution is followed by a batch normalization and incubation. These are all standard. So let's see the networks in detail. And we'll also see the code. So this is the architecture of the generator network. It contains these following blocks. We have the pre-residual block. So this is the pre-residual block. This. It has this 9, kernel size of 9, number of filters is 64, stride is 1. So this is the pre-residual block, and this is the post-residual block. There are 2 of them, 1, 2. The post-residual block has kernel size of 3, number of filters is 256, stride is 1. So this is the post-residual block. Then you have the residual block itself. So this is the residual block here. Okay. Now, then you have the upsampling block and the final convolution layer. So this is the upsampling block. What's the upsampling block? This is the final convolution layer. This is the upsampling block. Okay, this is the upsampling block. This is the upsampling block. I think this is the upsampling block. We'll see it in the code. But this, beg your pardon, this one is the post. I said before this one is the post residual block. The residual block stops here. The residual block starts from here and hence here. So this is the post residual block, and these 2 should be the upsampling block. Okay. So the pre-residual block contains a single 2D convolution layer and ReLU. And this is how it is defined: the input shape, the output shape. So we now have the number of filters is 64. So that's why we have the last component to be 64 here. And since the stride is still 1 and padding is the same, the shape is maintained. So the only thing that changes is from channel 3 channel, we move into 64 channel, if you may say, because that last component in the feature map is determined by the number of filters. Whatever value that is there will be the last value in the output shape. Okay, so you have the residual block. This is another important piece we'll look at in subsequent tutorials about the residual block, and we can demystify that and see what the residual block it's actually on. It's based on another paper in a ResNet paper, I think by Google. So it contains 2D convolution. Both layers are followed by a batch normalization with a value of momentum equals to 0.8. So let's see. So this is the residual block. So this residual block is repeated here a number of times, which you will see. And each of them, it's just constant. They all have 64 channels. They all have kernel size of 3, and they maintain the shape throughout. So this is what you have. You to be clearer by the time we get to the code. So the additional layer calculates the sum of the input tensor to the block and the output last batch normalization layer. So this is what I was saying. So this is the input, this one, the input to this residual block, and the last one here, the last here. So you have this element wise summation. Well, they made use of 16 residual blocks. 16 is an hyperparameters. We could play around with different numbers and see what the result looks like. Then you have the post residual block. It contains a 2D convolution layer, ReLU integration function. Convolution layer is followed by a batch normalization. Momentum of 0.8. So this is the configuration. So the filter is 64. So you can see we have 64 here. Stride is the same. Anytime stride is the same, anytime stride is 1 and padding is same, you will have the same width and height. So it will not change. Okay, so the upsampling block contains the deconvolution or the convolution transport. One upsampling layer. So here they didn't use the they use the upsampling layer. Sorry about that. And 1 2D convolution. So the upsampling takes in and multiply by 2. So you have based on size 2, so you just multiply it. You can see the width and the height turn to 2. It does not have anything to do with the channel or the filters. Okay. So they use 2 upsampling block in the generator, and you can play around with that. Essentially, your number of upsampling block is dependent on what your total width is going to be. So by the time you get to 256 by 256, you want to stop. If you want to get to 512 by 512, you can keep adding more upsampling layer, convolution layer, and you can keep adding your number of filters. The number of filters affect this. Okay. Then the configuration of the second upsampling block is still the same. The 2 doubles that. Then that's just that. This is in the generator network. So the last convolution layer, so this is where we now come back to our input image back to generate an image of shape. You can see here that we did not distort the shape, the square shape, because we're just using fully convolution. There's nothing like dense here, and that is found to be optimized for processing when you don't have to flatten the tensor, so you maintain the shape of the tensor throughout. So the last layer is 2D compilation. They use tan H, generate an image of this shape, which is our desired image. So we could play around with this. If you want it to be 512 by 512 or whatever, you could play around with that. So let's see the architecture of the discriminator. The discriminator is the simplest. It's just a binary classifier. It's a deep convolution. It contains 8 convolution blocks followed by 2 dense fully collected layers. So each convolution block is followed by batch normalization for normalization. There are also 2 dense layers at the end, which work as a classification block. So the last layer predicts the probability that it is belonging to real or fake. The detailed configuration of the discrimination is shown below. So this is it. So the same thing, filter 64, stride is the same, so it remains the same. The input layer, the input and output is the same. This is what we're giving it. This is the shape of our, we resize all our images to this. So we had another convolution. We're just keeping here we use a stride of 2, so that decreased our shape. So we have 256, it decreases by 2 because we're using a stride of 2. Then we're using a stride of 1, it remains the same, but we change the number of filters. Then we're using a stride of 2, so we decrease the width and the height, but we keep the number of filters. It's just a systematic way of constructing an architecture here. Then we increase the number of filters, we keep the shape, so it remains 64. Then we keep the filters, but we reduce the width and height by strides. So it's just like switching between filters and stride. That's the only thing that is switching here. So once you start with first increasing the filters and maintaining the shape. So 64 to 128, you carry the from here. First they increase the filters, then they maintain the filters and now decrease the shape. So the next thing, they increase the filters, maintain the shape, maintain the filters, decrease the shape, increase the filters, maintain the shape, maintain the filters, increase the shape. Good. So the objective function, the train SR GAN, is very important. So to train SR, there is an objective function, what you also call a loss function, so which we need to minimize. That's actually what we need to optimize. So the objective function is called the perpetual loss. That's what they were trying to tell us here in the loss here. So they use what they call the perpetual loss. Where did they mention it? And the loss function is adversary is content loss. This is a perpetual loss function, and it consists of, I think, the content loss and the adversary loss or something. So you see that, yeah. So this weighted sum of two loss functions. So we're doing composite optimization. So you have content loss, you have the adversary loss. So let's see the two loss. Although that should be a subject of another tutorial, we just quickly look through it, then we will not go deep into it. So the content loss, there are two types of content loss. You have the pixel-wide loss, the VGG loss. Like I said, we will not look into the details. So this is the pixel-wide loss. We'll look at that later on. Then the VGG loss, we'll look at that another time. Then we have the adversary loss. This adversary loss, we'll consider that later. So now, how do we now run the code? So let's see the code. There are certain requirements that needs to be installed, certain packages. They use Celibur 8 data set, and I run it also on my proprietary data. As you can see here, you will see here I use working on a project on B machine, so you can see what is generated. You can see the original, you can see the generated at epoch 900. My memory crashed, the Colab memory crashed. It's recommended that you train for more epochs to be able to get a better resolution generated. But even at 900 epochs, look at this. This is not bad. This is not bad at all. But you can look at it and say, oh, this is close to what you expect. That is close to what you expect. So I think I showed some more. Did I? Let me see if I show some more at other epochs. Okay, so I show some more. So let's see at 0. That's at 100 epochs. You see the resolution. See that 100. At 200, you see it's already taking some shape. At 400 epochs, it's already taking even a good performance. This is at 800, 500 or so. It's 600 epochs. You see this one is already picking it. Yeah, at 700 epochs we have 800 epochs. So, and I've showed the 900 before. Okay. So we see how that is. So it's just straightforward to train the network, and I love the way I recommend this book, Generative Adversarial Network by Kailash. I love the way the code for the book is written. I find it very easy to follow and to understand. So these are all the packages that you need. These are the packages you need. So we then start by defining them. I think I should just show you straight from my own. Okay, I'll still show us, but let's just see what they did there. So this is the architecture of the generator network in code, and they use Keras. So and they use the functional API. If you want to check in my channel, I think I have something on functional API, but it's pretty easy. Perform the following steps to implement the generator network. So define the hyperparameters. Parameters are values you play around with, but most often you just follow they often used standard in literature and published papers. You start with that and see if it works well on your problem. So this is the input shape for the generator. So you declare the input layer, so passes it to the next layer. So we had a pre-residual block, which we have showed the configuration. So this defines our pre-residual block. From here, what I highlighted defines our pre-residual block. So that defines our pre-residual block. Then using the functional API, we pass in the previous layer. This is the way we construct a functional network. So you pass it this way, then you store the result in another variable. Then because we are going to have 16 of residual block, we just put all the residual block in a function. So it takes in a layer, there are some hyperparameters of it, then you start defining that layer that you send as x. You pass it just a functional, you store it in a variable, you pass this to the next one, you store it in the same variable, you pass it to the next one, store it in, and do like that until you get to the end. Then you do the element wise, that which we mentioned before, which is this is pre-residual and this is the post-residual. So this does the element wise that I mentioned, element wise sum here. So that's what the hard layer does, and we see that the hard layers is imported from the Keras.layers. So this is in the Keras.layers we have this add layer. We also have the flattened there, so Keras.layers. Okay, so these are the hyperparameters of the residual block, and these define the residual block. So all we now need is just to call this 16 times. We just need this 16 times. So to be able to have it 16 times, so now add the 16 residual block using the residual block function that we have defined. So we just call the function, we pass in our pre-residual block, which is this gen1 in, we store that in the result in res. Okay, so we've already done the first one, so we need to do it for 15 times. So that's why we subtracted 1 from here. So we can now use for loop, the for loop, because after you have already done, you pass this res, this gen into it, it goes in as x, and it comes eventually with res, so it returns this res. But I'm a little bit confused here, because if it is going in, you're passing this gen1, so here will be the process Gen 1 on residual block, but you are still adding the pre-Gen 1. Is there any space for that here? Because this is Gen 1 and you are still adding it. That's not too clear to me. If somebody understands that, you can leave a comment below. Anyway, so you pass it through the residual block 15 more times and you eventually get this. I think it's always adding the previous ones. It's always adding the previous ones, maybe. Oh, so we're having element sum even in the residual block. Yeah, that is the truth. That is what we're saying. We keep having the element wise sum, that is the pre and the post. Yeah, so it makes sense now. So this is what is happening. This is the element wise, because I was wondering why we have the hard layer. So you have the pre, which is hex, and the post of after passing it through the residual block, the output of your x, then you do an element wise of it. But interesting architecture. I'm always surprised how people are able to reason out that kind of construction. We're still learning. The output of the pre-trained the output of the pre-residual block goes to the first residual block. Yeah, the output of the first residual goes to the second residual, and so on until the 16th. Yeah. Now, so we have the post residual block, and this is it. So what does it do? It just takes your output of res, which is the last one here, and you just pass it to this. This is the post residual block, and you define your Gen 2. You pass it to batch normalization. Then you now do again the element wise sum of the original Gen 1 here, the first one, and just the same thing that you're doing inside the ResNet. You now do it again with the final output after the post residual block. So you have the Gen 2, which is the final, and the Gen 1. So that is what this was saying. This is what this is in code, the element wise sum here. So that's what this is. So this is the post. This is the post residual block that was added. So that post residual block is this. So this in code corresponds to this representation, convolution batch net. This element wise sum is what you're seeing here. This is this of Gen 2, this one, and Gen 1. So of this, the output of this is Gen 2, goes in here, and this is the output of Gen 1. Interesting. Next, add an upsampling block as follows. So you have an upsampling block. Yeah. This pretty, so we pass your Gen 3 to the upsampling block. We look at this, add another one, the same thing, and final is there. So we have two upsampling block. So this is one, this is two. Those are the two, and this is the final convolution. You see, this is 9, 3, 1. So the final is 9. So that is the kernel side. 3 filters, 1. That's the stride. Okay. You will see that the 2 before is 256.31. The same thing, 256.31. So that is this. This is 256. Number of filters, kernel 3.1. So this block and this block are the same thing. So that is why they are having the same color. You see that they are using the same green to tell you that the architecture is the same. Does it make sense? Okay. So then that's all done. Once you have defined all the layers, so the final output is the activation. You put that in the output, then to form, you use the modal to the imported model. So then you put input equals the input layer, output equals the output, then you can give it a name. Okay. So this is the generator, the build generator. It's pretty the same thing. So you follow the functional. So you can just go through this. It's just the same way of building. Oh, sorry. This generator, they just put everything in a function. So they wrap the entire code in a function. That's what we have already gone through, and they return the model. So let's go through this discriminator. So the discriminator is start with the hyperparameters, the input shape, nothing different. The first convolution, the hyperparameters, the second convolution, the third, the fourth, the fifth, the sixth, the seventh, and they use the 8 convolutions. So these are all the 8 convolutions. 1, 2, 3, 4, 5, 6. This one. 1, 2, 3, 4, 5, 6, 7, 8. So after the 8, then you have the dense of 1024. Is 1024. Then you have the 1. Then you have sigmoid. Pretty straightforward. You have a sigmoid, and you form your model. That's all. So everything put together in a function. And there are some sub ones like VGG network. That's just standard, just pre-trained network. You can easily see this. To download a pre-trained network, this is just, you just use this. And this is not necessary. I don't know why they put this here. It wasn't used. So this is an error. This wasn't used. So the input, to extract the features, you just call the model on your input layer, and you can create your model with input with the input layer and the output to be your features. That's all. So everything put together in a function is this. Then you have the adversary loss. I'll just go through that briefly. We might have to continue from adversary loss. I think we just continue from the adversary loss in the next session. We'll look at that. So this is the compile, standard ways of compiling. You compile all the networks differently. You compile the networks. Then you have the adversary model, which I said we will look at in the next tutorial. Then you have the tensor board, just to log, and the training procedure is standard for GAN network. We will also look at this in standard when we're looking at the entire thing. So let me stop here. So in the next session we'll look at how we do the training and the adversary logs. Yeah, and saving the model. So, all right, thank you very much for listening, and do let us know what your comment are. Please give a thumb up if you enjoyed this and it's benefited you, and see you in the next one.